So my name is Bob Sinkovits. I'm the Director of Education here at the San Diego Supercomputer Center. And I'm going to be giving a very high-level talk on parallel computing concepts. If you want to follow along, take a look in the chat. I had posted the links to a PDF of the presentation and to a GitHub repo that I used to generate some of the figures. So this session is really intended for a very broad audience. So we're looking at anybody who currently, got too many messages popping up. For anybody who currently plans to run or is thinking about running applications on parallel computers, if you write proposals for computer time on campus clusters, nationally allocated systems, or other resources. So if we have any more senior PIs on the call, I know that a lot of you aren't directly involved in programming anymore, that you might be the one leading the group. You have graduate students, postdocs, and so on who are doing the actual computing, but you still need to understand the parallel computing concept so that you can write a good proposal. We're also looking at anybody who is purchasing time and compute resources and wants to maximize the return on investment. For example, if you're running in the cloud on AWS or Google Cloud or Azure, the same principles that we're going to be talking about here today apply there also. If you're thinking about purchasing hardware for your lab, and I'm sure this applies to a lot of you, if you're just curious about parallel computing. So why are we doing this training? So we've been involved here at SDSC and more broadly as part of Exceed. We've been doing training for decades, and very skilled people doing the training. A lot of great technical content, but we realize that a lot of the training that we do in parallel computing is targeted at people who write their own parallel applications, and it focuses on programmer topics. So again, all very valuable, but only if you're actually a programmer or developer. So things like MPI, OpenMP, CUDA, profiling, performance tuning. So as a consequence, we find that the end users who are not developers rarely or never get a proper introduction to parallel computing. But even if you don't write your own code, it's still important to understand the basic principles of parallel computing so that you can make the most effective use of valuable cyber infrastructure. So before we dive into the little bit of the technical content, we're going to address some of the myths of parallel computing. And the first one, and I hear this over and over, is that parallel computing is for astrophysicists, engineers, climate modelers, and others who are working in traditionally math-intensive fields. And that is, I hope many of you already know that this is incorrect. So when I first started at SDSC decades ago, that was partially true. Our user base was overwhelmingly astrophysicists and engineers. But today we find that nearly every field of research makes use of parallel computing. And this includes the social sciences, life sciences, arts and humanities, in addition to what we call the usual suspects, the chemists, physicists, engineers, and so on. Another myth that I hear of parallel computing is that throwing more hardware at a problem will automatically reduce the time to solution. And of course, first of all, parallel computing is only going to help if you already have an application that has been written to take advantage of parallel hardware. And even if you do have a parallel code, there's going to be an inherent limit on the scalability of that code. And there's one caveat though. A high throughput computing workload can use parallel computing to run many single core instances of an application to achieve near perfect scaling. And the third myth is that you need to be a programmer or a software to make use of parallel computing. And again, this was partially true. Maybe if you go back 25 years, there wasn't a whole lot of mature third-party software out there. If you were a computational chemist or a molecular biologist, you pretty much had to write your own. But now, most of the users of our parallel computers, they are not programmers. They're really using mature third-party software that's been developed elsewhere and made available to the community. So in a nutshell, most of you, and I think most of you here, are going to be using somebody else's code. So for example, if you're doing climate and weather modeling, you might use an application like WRF or MPAS or CESM. If you're doing molecular dynamics of biological systems, of proteins and lipids and other large complexes, you might be using AMBER or NAMD or GROMACS. If you're doing electronic structure calculations or computational chemistry, you're going to use codes like such as CP2K, GAMES, Gaussian, and others. And if you're constructing phylogenetic trees, you might use applications like RAXML and BEAST. So we find that for every user who's actually developing code, there are many who are using somebody else's code. So just going to give a very, very high level view of what a parallel computer is. So these modern clusters and parallel computers, they consist of multiple compute nodes, each connected together by a fast network. Each of these nodes typically contains one or more, typically 2 multi-core processors. In fact, all of you are probably being exposed to parallel computing every day, even if you're not aware of it, because your laptop probably has a multi-core processor in it. And there'll be multiple threads executing at the same time doing different tasks. So what I'm showing on the right here is the figure is a logical view of a supercomputer. This is the Expanse system here at SDSC. But if you see diagrams for the other machines that are available through Exceed, Stampede 2, Bridges 2, Anvil, Delta, and the other systems that are coming online, they'll all look pretty similar to this, where it's racks of hardware joined, racks of hardware, compute nodes, GPU nodes, that interact with each other through a high-speed network, typically Ethernet or InfiniBand. And in order to effectively use this hardware, we need applications that can parallelize so that it can run on multiple cores within a node or across multiple nodes. So getting into a little bit of the technical content. Getting into the technical content, we're going to talk just a little bit about processes and threads. So these are terms that you may have, that you may hear used periodically. You might be wondering what they are. A process, you could think of that as an instance of a program with access to its own memory, state, and file descriptors. So it can open and close files. Threads, these are lightweight entities that execute inside of a process. So every process is going to have at least one thread, and threads within a process can access shared memory. Okay, so if you try to do a search online for a description of threads and processes, they tend to be geared toward computer scientists. But I found a couple of resources that I think do a pretty good job of addressing the topic. So there's one thread that I found on Stack Overflow, which I think is a little bit on the nerdier side. It's really targeted more at programmers and developers, but I think there's a lot of valuable information in there. And if you want a lighter view, a more informal view of the difference between threads and processes, I think this second link does a pretty good job. So some of the key differences between processes and threads I'm highlighting here. So processes, they incur more overhead. They're heavier weight, but they're also more flexible. Multiple processes can be run within a compute node, or you can run across multiple compute nodes, what we call distributed memory parallelism. Threads are lighter weight. They incur less overhead. If you have an application that's threaded, you can also reduce the memory footprint. Since threads within a process all have access to the same pool of data, they could simultaneously access that same data structure. The limitation of threads, though, is that they're less flexible. So multiple threads associated with a process can only be run within a compute node, what we call shared memory parallelism. Okay, so I know that the description of processes and threads, it's still a little abstract. But I think that it's still important that you have a feel for processes and threads, because this is going to determine how and where you can run your applications. So what we call distributed memory applications, these are things that run across multiple nodes. This involves multiple processes, multiple instances of a program. Shared memory applications, threaded, should only be run on a single node. And we're going to talk about that in the next few slides about the performance implications there. Now, it gets a little more complicated when we get into what we call hybrid applications. So these are their applications that use a mix of processes and threading within the process. And if you're running one of these hybrid applications, which are becoming more and more common, you're going to need to consider the balance between threads and processes. And in all cases, when you're actually running these jobs on the supercomputers, you're going to need to consider how the processes and threads are mapped and bound to cores. So in this talk, it's very, very introductory. We're not actually getting into running applications, but in some other training that we have within SDSC and XC, we do cover the details of launching jobs and how you can make sure that threads are bound to particular CPUs, that they don't migrate, and that you can, and this will help you to improve the performance of your application. And then finally, if you're aware of threads and processes, this will help you to understand how your code is utilizing the hardware and identify some common performance issues. So I'm gonna touch very briefly on a couple of topics. I mentioned these earlier, MPI and OpenMP. We're not here to teach you MPI and OpenMP today. If you're not a programmer or developer, these aren't things that you need to learn. But I think that you all need to be aware of, you need to be aware of these topics. So MPI is a standard for parallelizing C, C++, and Fortran code so that it can run on distributed memory, multiple compute node systems. So while it's not officially adopted by any of the major standards bodies, it's really become the de facto standard, i.e. it's pretty much everyone uses it to develop parallel applications. Now, what gets a little confusing is you'll hear about MPI, but then you may also hear of things called like OpenMPI or MVAPIC or MPIC. These are just different implementations of MPI. So MPI is the standard, it describes the API, but OpenMPI, MVAPIC, and MPIC, along with vendor-supported versions of MPI, are the actual implementations. Now, MPI applications, they can be run within a shared memory node. All widely used MPI implementations are optimized to take advantage of that faster communications that you're going to have within a node relative to communicating across nodes. One of the beautiful things about MPI is that it's portable and it can be used anywhere. Back in the early days of parallel computing, it was a lot harder. Each vendor might have its own way of doing parallelism. That made it really hard to write multiple code. You tended to be tied to a particular resource. But like I said, MPI is portable. You can use it anywhere. Well, once you have a properly written MPI application, you can port it to any of the systems. And then finally, though, I want to mention that MPI is often synonymous with distributed memory parallelization, but there are other options out there. For example, Charm++ is used to parallelize NAMD, one of the most popular molecular dynamics applications. There's the UPC languages that are developed at National Labs, X10, and others. So even though MPI is going to be predominant, just be aware that there are other ways to parallelize the codes. So I said in the beginning that this talk is not going to be geared at programmers and developers. It's going to be really looking at the end users. So bear with me. If you're not interested in programming, you can ignore what's going on the left-hand side of the screen. But I figured it would be useful for you to at least see an example of what MPI is. So if you've ever taken a programming class, you've probably done a Hello World program. So I'm showing over here on the left-hand side in the gray box, a very, very simple C program that prints Hello World to the screen. Now, an MPI version of this code And I've highlighted all of the new code in bold and purple. It shows what we would do if we wanted to parallelize this application so that each process writes out its name, its ID, and hello world to the terminal. So we're not going to go through all of the content here. You could see though that it's pretty dense. MPI applications, they look a lot like they look a lot like C programs. They tend to be fairly abstract. Again, if you're not a programmer or an application developer, you don't need to know MPI. You just need to be aware that it exists. And if you need to build your own executables, and by that I mean you're downloading somebody's source code, you need to build the application to run on a computer, then you need to make sure that you're using the appropriate wrappers and compilers so that you link in the MPI libraries. Okay, OpenMP, switching gears, is an application programming interface for shared memory, doing parallelization within a node, parallel programming in C, C++, and Fortran. So this is if we want to do thread level parallelization. OpenMP provides a collection of compiler directives, library routines, and environment variables. Importantly, OpenMP is supported by all of the major compilers, including the IBM, Intel, GCC, that's the GNU compiler collection, PGI, and the AMD optimizing C and C++ compilers, AOCC. And we have the latter, so we have GCC, PGI, and the AOCC available here on the Expanse supercomputer at SDSC, and you will find the rest of these on many of the Expanse allocated systems. Like MPI, what makes OpenMP so powerful is that it's portable and it can be used anywhere. And also, like MPI tends to be synonymous with distributed memory parallelization, OpenMP is often synonymous with shared memory parallelization, but be aware that there are a lot of other options out there. There's a programming language called Silk, which is an extension of C to handle multiple threads. There's something called POSIX threads or P threads, and there's specialized libraries for Python, R, and other programming languages that allow you to do shared memory or threaded parallelism. So again, if you're not a programmer, you don't need to know this. Feel free to ignore what's going on the left-hand side of the screen. But if you are a programmer, you might recognize what's going on here. We're taking two arrays, A and B, we're initializing them. And then in the loop at the bottom, we are adding them element by element. Now, applications parallelized using OpenMP tend to be much more readable than MPI programs, since they often involve relatively minor changes to the code. So you can see here that I just defined a few variables, and at the bottom, I'm using a pragma, if this was C code, or a directive, if this was Fortran code, to parallelize that loop. Again, we don't need to get into the details, but you just need to be aware of OpenMP, that it exists. And like MPI applications, if you're building your executable from source code, you need to make sure that you use the appropriate compiler flags. And if you look at the user guide for Expanse or any of the other Xseed allocated resources, you'll find instructions on how to do this for each of the major compilers that they support. So to bring that all together, kind of the big picture. On the left-hand side, we're talking about MPI. We use MPI to manage multiple processes. And then MPitch and MVAPitch and OpenMPI and the vendor implementations, these are all specific implementations of MPI. Now, one point of confusion here is, whether or not these different implementations do different things. They don't. They all support the MPI standards. So you don't need to write, so code doesn't need to be written for MPitch or MVAPitch or OpenMPI. Like I said, MPI is a standard. MPI codes should run everywhere. On the right-hand side, when we're talking about threads, we can manage multiple threads using OpenMP. And then OpenMP is implemented by the compilers, by GCC, Intel, AOCC, and others. Right, so things get a little more complicated in that we can have these hybrid applications. So many modern parallel applications are built using a hybrid approach to take advantage of both distributed and shared memory. So this typically involves MPI and OpenMP. So MPI to break up your code into multiple processes, and then OpenMP to execute multiple threads within each process. Hybrid codes, they have some advantages over purely shared or distributed memory applications. So shared memory apps, they have limited scalability. They may have limited scalability within a node, and they can definitely not run across multiple nodes. Distributed memory apps, on the other hand, may have higher memory requirements and more overhead when running within a node. So typically, we're going to try to use processes to parallelize across nodes, threads to parallelize within nodes. So we're going to take a look at a very, very simplified parallel computer. Of course, this is much smaller than anything you would actually encounter. We're just going to use this to walk through a couple of examples. So let's consider a very simple system. It just contains two compute nodes, each with 16 cores, and that these nodes can talk to each other through a network. The interconnect, this could be typically Ethernet or InfiniBand. So what I'm showing here in the large box in gray is the node, and within it we have our 16 compute cores. So if we're running a purely message passing application, these are applications that say have been parallelized using MPI. Typically, we're going to run one process per core. So I'm showing the processes here in orange. So this is an example of an application running 32 processes across two 16-core nodes. Now, if we have a purely threaded application, let's say it's been parallelized using only OpenMP or Silk or pthreads or the various options in Python or R, we're going to be restricted to running within a single node. So in this case, I'm showing this threaded application, single process, but with 16 threads running across 16 cores. And I have a little caveat here at the bottom. Technically, any programming model can be mapped to any hardware. But what we find, though, is in practice, threaded applications really need to be run within a single node for best performance. Okay, when we get into hybrid applications, again, typically MPI plus OpenMP, but other combinations are possible. Here we're showing a case where we have 2 processes per node and 8 threads per process. A typical scenario is to run 1 process per node and then use threads within a node, but this is becoming a little less common. I would say in the past, when the nodes weren't quite as fat, when they contained maybe 12 or 16 or even 32 cores, this is the way we would typically run a hybrid application. But now the modern multi-core processors with 16 cores per processor, 2 processors per node for a total of 128 cores, the next generation of AMD hardware is going to have even more cores. You're going to find that we may not always want to do this, that we may want to go back to a case where we're running multiple processes per node and multiple threads within a process. So this is where it gets a little tricky. If you're running these hybrid applications, you're going to need to think about how to choose the best balance between cores and threads. And the question is, how do we choose this balance? So going back to our hypothetical parallel computer with 16 cores per node, now we can do everything from, on the left-hand side, 1 process per node with 16 threads per process, to the other extreme of 1 process per core. And I'm going to say the only way to really know is to benchmark your code, look at both the runtime for different combinations and memory usage. So we're going to switch gears a little bit, talk about the scalability of parallel applications before we wrap up with some benchmarking. So if you know one law in parallel computing, it's probably Amdahl's law. So this is you could think of Amdahl's law as being the E equals MC squared or the F equals MA of parallel computing. And Amdahl's law tells you the absolute limit on the speed up of a code as a function of the proportion of the code that can be parallelized and the number of processes. So as I mentioned, this is truly the most fundamental law of parallel computing. If you only memorize one law, this is the one to know. So let's say that P is the fraction of the code that can be parallelized. And when I say fraction of the code, I don't mean the number of functions or routines, the number of lines of software. I mean the execution time of the code. So if we have an operation, let's say it's the multiplying two matrices or calculating eigenvalues. You know, if that's an operation that could be done in parallel, that's parallel content. S is the fraction of the code that must be run sequentially. So there may be a lot of operations that need to be that just can't be parallelized. Let's say it's the it's the reading of an input file in certain cases, or the calculation of result that needs to be done once, but then broadcast to all the processes. So that's our sequential fraction. And of course, the potentially parallelizable fraction of the code plus the fraction of the code that must be run sequentially has to equal 1. And n is the number of processes. So the theoretical speedup that we could get from running on n processors is 1 over 1 minus p plus p over n. So as the number of processors goes to infinity, the theoretical speedup is going to depend only on the proportion of the parallel content. So if we go back to Amdahl's law, we let n go to infinity, we end up with 1 over 1 minus p, or 1 over s. So looking at it right now, you're probably thinking, oh, that's not so bad. But as we'll show in the next slide, it doesn't take much serial content to quickly impact the speed up. So what I'm showing here is the speed up of code, how many times faster it runs as we start running on more cores. And I'm showing this for 4 different cases, for parallel content of 50%, 75%, 90%, and 95%. So the first thing that you want, the first big takeaway here is that the maximum speed up that you get, even if you have 95% parallelizable content, it's only a 20x. And that's only a small fraction of a, that's only a small fraction of the compute power on a single compute node. Now, if we go a little bit further, you're thinking, let's say we have a code with 99% parallel content. If we look at that table on the right, we see even if we have only 1% serial content, the maximum speedup that we get by throwing thousands and thousands of processors at this problem is only 100x. So again, that's still less than a full compute node and not anywhere close to the full power of a multi-node supercomputer. And not only that, you're probably not going to get that 100x speedup. So I have an arrow on the figure which indicates running that code with 99% parallel content on 128 cores, or 1 Expanse or Bridges 2 compute node. So we can see here we're using 128 cores, but we only got a 60x speedup. So that's really a terrible use of that computer. You're wasting a lot of hardware, and we're going to talk in the next few slides about, toward the end of the talk, where we should be running. So you can see just that little bit of serial content can really impact your scalability. Now, on top of that, in addition to Amdahl's law, there are other factors that affect scalability. So keep in mind that Amdahl's law is a theoretical upper limit on speed up. So we're going to have other things. We're going to have the communications overhead. We're going to have limitations due to problem size, let's say we're looking at a problem of a fixed size, we can only split it up so far and distribute it across multiple threads of processes. We're also going to run into a problem of uneven load balancing, where all of the processes aren't doing the same amount of work. So in real life applications that involve communications, if there's synchronization events, say where all the threads of the processes have to complete their work before we move on, or if we have what we call irregular problems, instead of nice Cartesian grids like I'll be showing in next few slides, but irregular domains, complex geometries, our speed up can be much less than predicted by Amdahl's law. So taking a look at load balancing. So when we parallelize a code, we need to take the computational work, we need to divide it into chunks that could be executed independently. Now they may need to communicate occasionally, but it's that division of work that allows us to take advantage of a parallel computer. So if the work cannot be distributed evenly, then processors are going to sit idle, waiting for the longest chunk to finish. So I'm showing 4 tasks here. That these could be processes, say parallelization done using MPI or threads, that the concept is the same. But imagine that the blue bar represents the time that each of those processes is busy, and then the red stripe blocks are idle time. So let's say we begin our calculation, we assign a chunk of work to tasks 0, 1, 2, and 3. We see that task 2 takes a little bit longer than everyone else. So task 0, task 1, and task 3, they're going to be sitting there. They're going to be idle, just waiting until task 2 finishes, until we get to one of these synchronization points where all the tasks must complete before proceeding. Let's say processes have to exchange newly computed results, or threads must finish updating the shared array. Then after that synchronization point, let's say we assign new chunks of work. And here the situation is a little bit different. In this case, task 1 got assigned the biggest chunk. And tasks 0, 2, and 3 had shorter chunks. So now they're all going to sit idle, waiting for task 1 to complete. So again, this is one of the factors that's going to impact the scalability of the code. Another one is communications overhead. So if you're doing something like computational fluid dynamics, magnetohydrodynamics, so essentially simulations of plasmas, climate and weather simulations, these all involve solving systems of partial differential equations. And the way we do that computationally is we will discretize our domain. We will do the calculations on a grid. And if we want to do this in parallel, we need to take that grid and distribute it across multiple processes. So in this case, and this of course is an unrealistically small problem, but imagine that we have a 16 by 16 grid, and we're going to divide it into 4 8 by 8 chunks that are distributed across the process. Now let's assume that each cell is updated using the values of the 4 neighboring cells. So for a cell that's within the interior of each chunk, these calculations can be done within each process. So I've highlighted one cell in each of those four chunks, highlighted with red, and I show in blue the 4 neighboring cells that it needs to get data from. Now it gets a little more complicated for the cells that are at the boundaries of the chunks. So the data belonging to the neighboring processes is needed. So to accommodate this, we need a halo of ghost cells, as we call them, and data must be communicated between processes. And that data communications, it takes time. So this data movement, it's going to depend on both the latency and the bandwidth of the network. So latency is essentially how long it takes that first bit of information to be transferred. Bandwidth is the rate at which you can transfer the data. And this communication, it's going to introduce overhead, and it's going to further cut into the scalability of your application. So to show what the communication pattern would look like, if we consider the two chunks on the top, the one on the upper left is going to pass that column of dark blue cells over to the over to the process executing the chunk in the upper right. And that's going to be held in the ghost cells. Similarly, the chunk in the upper right is going to communicate a column of data over to the process on the upper left. So now after we do that communications, we can finish the calculations for all of those cells that are around the edge of the domain. And then just to show you what the rest of the communication pattern looks like. So again, this communications overhead is going to impact the performance and the scalability. So at this point, you're probably ready to throw up your hands and think, wow, how am I, with everything working against me, these hard limits imposed by Amdahl's law, load imbalance, communications overhead, all these things that affect the scalability. How is anybody ever going to use all of the cores on a single modern compute node, let alone the full power of large supercomputers? So first, the reality is that most parallel applications are not going to scale to thousands or even hundreds of cores. In fact, if you have an account on any of the Exceed machines, and you take a look at the queue, you will see that there are a lot of jobs in there that are using anywhere from a single core to a single node. And then second of all, there are applications that do achieve high scalability, but they employ several strategies. So first of all, you can grow the problem size with the number of cores or nodes. So let's say we're doing molecular dynamics simulation of a material. We're originally, say, working with 1 million atoms or 1 million particles. We're not going to try to take that problem and run it across 1,000 compute nodes. We're going to grow that. We're going to solve a much larger problem. Maybe looking at billions or potentially trillions of atoms. And if you want to know a little bit more about the scaling that you see as you increase problem size with the number of nodes, you can look into Gustafson's law. I didn't have a chance to go into it here. It's a little more technical, but it addresses this issue. Another thing we can do is overlap communications with computations. So while we're doing the calculations on those interior cells of our domains, we could be at the same time communicating data between processes so that by the time we get to those cells around the boundary, we have the data that we need. We can use dynamic load balancing to assign work to cores as they become idle. And we can also do computations that increase the ratio of computation to communications. So for example, if we're doing computational fluid dynamics, and we decide to go to the next step and look at combustion, where we actually have to take into account the chemistry that's going on in the cells, that's very computationally intensive, and that increases our ratio of computation to communication, and that code will likely be more scalable. So running parallel applications. So far we covered the basics parallel computing. We talked a little bit about hardware, threads, processes, hybrid applications, the implementations, Amdahl's law, and other factors that affect scalability. So we've looked at a lot of theory and backgrounds. This is great. I think you all need to know this. But the big question is, as an end user running somebody else's application on a supercomputer, how many processes do we use when we run that application? And the only way to definitively answer that question is to perform a scaling study where a representative problem is run on different numbers of processes. And by representative, we mean a problem of the same size, say the same grid dimension, the number of particles, number of images, number of genomes, et cetera, the same level of complexity. So if you're a computational chemist, the level of theory. If you're doing other applications, the type of analysis, the type of physics that's being treated. So your representative problem has to look like the research problem that you want to solve. So of course, you're not going to take a full climate simulation, run it for 100 years in order to do the benchmarking, but you could take that problem and run it for just a few time steps in order to get a feel for how the runtime will grow as you do more time steps. So presenting scaling results. We see this a lot in the allocation process. In fact, Exceed has a great webinar that they do a few times a year, where they get into this issue of how you present your scaling data. So believe it or not, these plots on the left and right-hand side are scaling curves for two different codes with different scalability. But the way that it's being presented, it's really hard to tell which one is better because the timings at large core counts are indistinguishable. So the right way to present the scaling data is, instead of using linear axes, to use log axes. First of all, look at the different time scales for on the left axis for the two plots. The example on the left is something that you're never going to see, that this is a perfectly scalable code. We could see that the red line plotted in this log-log scale is linear. I've included a solid black line as a guide to show what linear scaling should be. I've also plotted the parallel efficiency. So this is the speed up divided by the number of processes. Basically, this means that we're running perfectly efficiently as we use more cores of processes. So on the right, and again, this is the same data that we're seeing on the previous slide, that this is showing a more realistic code that, you know, as we increase the core count to 2 to 4 to 8, it runs a little bit slower. We can see that the parallel efficiency, though, tends to drop pretty quickly after about 8 cores. And by the time we get to running on 128 cores, we can see that we've only achieved a parallel efficiency of about 20%. Okay, so where should you be on this scaling curve? So we're gonna cover a couple of guidelines in these last few slides. So if your work is not particularly sensitive to the time to complete a single run, consider using a core count that's at or very close to 100% efficiency, even if that means running on a single core. So I know if you have a calculation that's going to take a long time, you don't want to wait days or weeks for it. But if you need to do many calculations and you really don't care about the time for any single calculation to be completed, but you're more interested in the time to complete that entire workload, you should really be running out here, you know, in or close to linear scaling regime, where you're getting where you're getting parallel efficiency that's say 80% or better. And this especially makes sense for parameter sweep workloads. Let's say where you're doing the same calculation many times, but with different sets of inputs. Okay, sometimes it's okay to go a little bit further out on that scaling curve. If the job would take an unreasonably long time at lower core counts, or if the shorter time to solution helps you make progress in your research. So if you have a code that does not have checkpoint restart capabilities, that means that you can stop, you can save the state of the code, read that back in and continue. Or the runtime would exceed queue limits, you may have no choice but to run at higher core counts. And then sometimes it's okay to go even further out. So let's say that you have calculations that need to be run on a regular schedule. Say you're collecting data every day, it needs to be processed overnight. The analysis has to be available in the morning. Sure, then you can run at lower core counts. Or if it's something that's absolutely critical, let's say that you're doing tornado or tsunami prediction, I would use as many cores as you can to get the absolute best performance, even if it impacts your parallel efficiency. Again, though, most of you are not going to be doing that. You're going to be doing scientific workloads where time to solution is not as critical. So you should be running it at a high parallel efficiency. Let me just check the chat. So there's a question, is it possible to do this on Exceed machines where we charge per node rather than per core, such as Stampede 2? No, so yeah, the different Exceed resources are operated in different ways. Expanse and Comet before it and Bridges 2 all allow the shared nodes. But on Stampede 2, you just need to use the entire node. And Stampede 2 is also looking at a little bit of a different user base. It was designed for highly scalable applications. And yeah, and the second part of the question, can we do this without wasting allocated compute time? If you're running in a shared queue on Expanse or Bridges 2, you would only be charged for the compute cores that you requested. So let's say you requested 8 cores, somebody else is using the rest of that node, you're only charged for the 8. Whereas on Stampede, since it's allocated by the node, once you grab that node, as far as the accounting goes, they don't care what you do with it. You could be using 1 core, you could be using all the cores. You're going to have the same charge against your allocation. And then other considerations, I'm just going to go over this very quickly. But sometimes you have an application that has a large memory footprint. So typically, when you submit a job, you can request memory in proportion to the core count. So we'll go to the example again of Expanse, where we have 256 gigabytes of memory per standard node and 128 cores. So that means that we have 2 gigabytes available per core. But what if I have an application with a really large memory footprint where I need 4 gigabytes or 8 gigabytes per core? And in that case, sorry, per process. In that case, you're just going to have to request more resources. I'm going to refer you to the user guides for bridges and Expanse for the right way to do that. But yeah, you may be stuck just having to ask for more cores, get poor scaling, and you can also use specialized large memory nodes. So just about done here. We've only scratched the surface. We didn't talk about how to actually run jobs or do the accounting or so on. So first of all, Exceed and SDSC have a lot of other training resources covering a wide range of topics. I have links here for Exceed and for SDSC. And then the user guides for these nationally allocated resources contain all of the practical information that you're going to need on the job submission, counting, and compilation, and data movement, the available software. And a lot of this is site specific. So I'm going to say, go to the go to those user guides for all of that information. And for a lot of this content that's available on Exceed, you need a user portal account, but you can create one of those for free and it only takes a couple of minutes. So in conclusion, I hope everybody's come away, realizing that parallel computing is for everyone who wants to accomplish more research and solve more challenging problems. It doesn't matter what your domain is. In fact, at least within Exceed, we've made a real strong effort over the last 10 years to make parallel computing more accessible to everyone outside of the usual suspects, the computational chemists and astrophysicists. So if you're from the social sciences, the arts and humanities, life sciences, absolutely, you can use these resources. Kind of beat this home through the entire talk, but you don't need to be a programmer to use parallel computers, but you do need to know some of the fundamentals to effectively use a parallel computer. A little bit of the technical content: processes are instances of programs, threads are run within a process and access shared data. MPI and OpenMP are the most common ways that you'll see to parallelize codes. Talk a little bit about scalability. Amdahl's law gives you an absolute upper limit on scalability, but there are other factors that affect scalability: load imbalance, communication overhead, and so on. And then finally, know how to display your scaling data. This is particularly important if you are submitting a proposal to Exceed or other organizations that allocate computer time, and know how to choose your core counts, take into consideration memory footprint, time to solution, and so on. And then we have this in the chat already, but if you're interested in the Jupyter notebooks that I use to create some of the figures in the presentation, particularly for the scaling plots or for Amdahl's law, they're available in this GitHub repo. In fact, you might find this very useful if you're in the process or planning to write an Exceed proposal. You could take my notebooks and just plug your own numbers in there. And with that, I'm all done. I'm happy to take any questions. Okay, so let me scroll back through the questions. Okay, so I see Quick question here from Abhishek. Could you explain what is the difference between strong and weak scaling, and when is each one relevant? Yes, yeah, so yeah, good, great question. I'll go into that a little bit more detail next time I do this talk. So strong scaling is when you take a problem of a fixed size and you run it on increasing numbers of processor cores. So let's say I'm doing a molecular dynamics simulation with 10 million atoms, or a CFD calculation with 100 million grid cells. So I'm taking that same problem, I'm running on 1 core, 2 core, 4 core, 8 core, and so on. Weak scaling is where I allow the program to grow as I use more nodes. So let's say I'm running a million particle molecular dynamics simulation on 1 node, and then 2 million on 2 nodes, and 4 million on 4 nodes, and so on and so on. And in that case, perfect weak scaling would be as if we see the runtime remain constant as the size of the problem and the number of processes is increased. And then finally, there's a question here from Jibo Liu. If I could give a short introduction and application about hyperthreading and how it works for MPI and OpenMP. Yeah, so I didn't mention hyperthreading. That's a hardware topic. But a lot of modern processes allow you to run what they call 2 hardware threads on each compute core. Now, to you as an end user, that's just going to appear as an additional compute core. So, for example, on Expanse, we have 128 physical CPUs per node. But if we turned on hyperthreading, it would look like 256. So the hyperthreading has applications for typically for business applications, but for a lot of HPC applications, we turn it off. So basically, it would just look to you like you had twice as many cores, and you would program in exactly the same way. And then finally, question here from Vincent. Is there any resource that you recommend that goes into more details about parallelization without assuming prior knowledge? You know, off the top of my head, I don't know, but I am going to, look into that. And if you could do me a favor and send me an email, and I will follow up with you later. And then there's a question from Tom Laredo. How do GPUs fit into this? Is it basically threading with specialized compilers? Yes, so you could think of GPUs as being massively multi-threaded hardware. I really didn't get into this. You don't just, yeah, there is a special compiler that is used in order to generate code to run on the GPUs. And how do GPUs fit into this? So when you're using the GPU, generally you're going to have that entire GPU will be allocated to you. There's no sharing of a GPU, but everything that we talked about in terms of scalability, if you have a multi-GPU application, you would want to do the same thing. You would want to do a benchmarking and scaling study to see how many GPUs you should be running on. And there's a question here from George Switzer. Are there additional considerations necessary when working with commercial code or other purchase software solutions where the user may not have access to the source? I think the best answer is really no. And in fact, for the most part, if you're using open source codes, such as Amber and NAMD and Romax and games and CP2K and so forth, you're probably not going to build it from source. That's something where that's a case where our user services will build those applications, making sure to use the best MPI libraries and compiler options, get performance. So I would say as far as an end user, there are really no other considerations. except other than possibly licensing. You need to make sure that the license is available for what we call, if you're going to be running on our resources, you probably want to have a floating license so that you're not tied to any particular compute node. But otherwise, everything else that I said, as an end user, I think applies. And I'm going to see if I could answer a few more questions before we run out of time. Lost my cursor.
Bob, did you actually answer a question regarding, let's see, is it possible to do this on Exceed machines where we are charged per node? Did you answer that?
Yep, I got that one already.
Okay, awesome, just checking.
Okay, so we're actually at the top of the hour, but I'm happy to continue answering questions for anybody who wants to stick around. Okay, so there's a question from Yogesh. How to identify dependencies in process and threads? Do we have a tool for the same? Trying to think how to answer that. There are, so I think by dependencies, you're talking about processes that need to communicate data, that need to exchange data, or threads that need to synchronize. So there are tools out there. There are profiling tools. I think the most powerful one I could think of is called Tau, T-A-U, and that will really dive into the into those interactions. It's much more advanced. As an end user, you're probably not concerned with that, but if you are developing your own code, that's something that you would want to follow up on. And we probably have training for that within Exceed. And great. And if there's anybody whose question I missed, please post it into the chat. I think I got everybody. Okay, well, if there are no other questions, I'm going to, okay. Quick question from Ali Smith. For Expanse, can you run parallel jobs on the shared node? Yes, absolutely. So when you decide to run a job on a shared node, you can choose anything from one core up to all the cores in that node. So let's say you have an application that very common, say with computational chemistry, where it only scales to 8 or 16 cores. Yes, you can submit a job and just request those 16 cores. And also you can, within a node, you can run MPI or threaded applications. Okay, can MPI be used for peer-to-peer compute? Mario, I'm sorry, that's, I don't know enough about peer-to-peer computing to answer that. But so I'll just stop there and avoid giving an incorrect answer. Okay, and then there's another question from Vincent. I understand the theoretical difference between process and thread, but some codes are not easy to define as either. Is there a way to know if a piece of code is a process or thread? Yes, so where to put it? So a chunk of code isn't exactly a process or a thread. It's the execution of that code. So if the code, say, had been parallelized using MPI, there will be multiple processes. And while that's running, if you log into that node and execute top or htop, you will see each of those individual processes. They each have a process ID associated with it. If you want to see the threads, at least within top and htop, there's a way to turn on thread viewing. You just type capital H at the command line, and it will show you the threads that are executing within that process. Now, if you have access to the source code, of course, you can just go in there and you can look for calls the MPI library or OpenMP directives. Yes, and thanks, Nicole. Less than one full node for shared. Yeah, I should have pointed out earlier, but when you're running in the shared node, I think that was answering Ali's question. There are 128 cores per node. You can request anywhere from 1 to 127. And if you use all 128, then you would just be in the regular queue. All right, and question from Ed Hall. Ed, that is a fantastic question. If you use a subset of cores on a node of Expanse, but all of the memory, are you charged for all of the cores? Yes, you are. We may have a presentation on this somewhere. Slurm has a fairly involved way of doing the charging. So yes, you can get memory in proportion to the cores, but let's say that you have a serial code. It just uses one core, but it needs all of that memory. You are going to be charged for the entire node. That said, though, if you request one core and all the memory, those other cores are going to be available for somebody else to use, assuming that there was enough memory left over. So Ed, if you have any questions, I know you're a campus champion, I think at Virginia. I could put you in touch with with one of our very talented sysadmins who can go into a lot more detail on that. Great, and thank you everybody for the kind comments. And yes, and Nicole, thanks for putting that in there. So, in this talk, we didn't have a chance to get into the specifics of any machine, but yeah, if you go to our user guide, you'll see all of the detail on the different queues or partitions that are available. Right, if that is it, if there are no more questions, we will go ahead and wrap things up. Thank you so much, everybody, and look forward to seeing you at future training events.